Hello, good afternoon. Unit 6, covalent bonding. First of all, covalent bond. Covalent bonding, this unit is under BSc first year, chemistry, PHEM 101, theory, uh, under Tribhuvan University, Institute of Science and Technology, BSc first year. Okay, covalent bonds, the bond formed by sharing of electrons between atoms is called covalent bond. Covalency refers to the number of electron pairs an atom shares with other atoms to form covalent bonds in a molecule. It is number of electrons shared by an atom with other atoms to form a molecule. That is, it is number of covalent bonds formed by an atom with other atoms in a molecule. Covalency of an atom is equal to number of unpaired electrons present in atomic orbitals. Variable covalency. Most p block elements shows more than one covalency, that is variable covalency. However, elements of second period, nitrogen, oxygen, and fluorine, do not show variable covalency due to absence of vacant d orbital at similar energy level. However, elements of higher periods exhibit variable covalency due to presence of vacant d orbitals at similar energy levels. Nitrogen shows only 3 covalency and phosphorus shows 3 and 5 covalency due to unpaired electrons, 3 in ground state but in 5 in the excited state. Properties of covalent compounds, physical state. Covalent compounds exist in solid, gas, and liquid, high molecule weight. Compounds have strong van der Waals force, that is, solid state. Low molecular weight compounds have weak van der Waals force, that is, gaseous state. Likewise, intermediate weight compounds have intermediate van der Waals force, that is, liquid state. But covalent compounds having the 2 or 3 dimensional giant form like diamond, graphite, silica always exist in solid. Melting point and boiling point. The covalent compounds having molecular form have low melting point and boiling point due to breaking of weak van der Waals force of attraction. However, covalent compounds having 2 or 3 dimensional giant form, diamond, graphite, silica, have extremely high melting point and boiling point due to breaking of strong van der Waals force of 2 or 3 dimensional network of covalent compounds. Electrical conductor. Covalent compounds are bad conductor of electricity due to absence of free electron and free ions, but some exception, graphite, black phosphorus. Solubility. Covalent compounds are generally soluble in non-polar solvents and insoluble in the polar solvents. Theories of covalent bonding. 3 types of theories of covalent bonding. Valency bond theory, valence electron pair repulsion theory, molecular orbital theory. First of all, valency bond theory, DVT. It was proposed by Hayter and London. According to BBT, the covalent bond is formed by overlapping by atomic orbitals, each containing unpaired electrons. Later on, this theory was explained. Pauling and Slatin to explain the directional nature of covalent bond and shape geometry of covalent molecule. Postulates of brevity. A covalent bond is formed by overlapping on-pair electrons. The greater the extent of overlapping of the atomic orbitals, the stronger is the covalent bond formed. That is, small orbitals from stronger bond and large orbitals from weak bond. Number of covalent bonds formed by an atom with other atom are equal to number of on-pair electrons present in atomic orbitals. Resonancy play important role in valence bond theory. Pair electrons do not form covalent bonds. However, it can form covalent if it is made on pair by excitation. A covalent bond is formed in the direction in which electron density are maximum. That's why covalent bond is directional in nature. Depending upon the way of overlap, two types of covalent bonds form, namely sigma bond and pi bond. Limitation of valence bond theory. The existence of coordinate bond is ruled out, in which both electrons come from only one atom. It does not explain the paramagnetic nature of some molecules like oxygen. It does not explain the formation of molecular ion like hydrogen, helium, etc. Resonancy, representation of a molecule by two or more to Lewis structure is called resonancy, and different Lewis structure are called resonance structure or canonical forms. The true structure of the molecule which resonates between the canonical forms is called resonancy hybrid. See, in this case of ozone, this is the resonance structure of canonical form of ozone. Hybridization, mixing of atomic orbitals of valence shell of central atom to produce new kinds of orbitals having equivalent energy is called hybridization, and new orbitals also called hybrid orbitals. Rules of hybridization, it is atomic orbitals of valence shell of central atom that participate in hybridization. The atomic orbitals participating in hybridization should have approximate same energy. Number of hybrid orbitals formed are equal to number of atomic orbitals. Hybrid orbitals always form sigma bonds and never form pi bond. The atomic orbitals that have to form pi bonds do not hybridization. Three types of atomic orbitals undergo hybridization. Atomic orbitals containing on-pair electrons, atomic orbitals containing on-pair electrons and pair electrons. Vacant atomic orbitals, hybrid orbitals has one larger and another lobe smaller. Only larger lobe participate in bonding. This is the SP hybrid, SD hybrid, SPT hybrid. Shape of covalent molecules depends on types of hybridization involved in the central atom and lone pairs, bond pairs, that is number of hybrid orbitals formed. Sum of the lone pairs and bond pairs number of hybrid orbitals, hybridization, shape, angle. 2 SP hybridization, linear 180, 3 SP2 hybridization, triangular. Four SP tetrahedral, 5 sp3d, dsp3, triangular, bipyramid, 6 sp3d2, d2sp3, octahedral, 90, 7 sp3d3, pentagonal bipyramid, dsp2, square corner. Key features of hybridization: atomic orbitals with equal energies undergo hybridization. The number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. It is not necessary that all the half-filled orbitals must participate in hybridization. Even completely filled orbitals with slightly different energies can also participate. Hybridization happens only during the bone formation and do not in isolated gaseous atom. The shape of the molecule can be predicted if the hybridization of the molecule is known. The bigger lobe of the hybrid orbital always has a positive sign, while the smaller lobe on the opposite side has a negative sign. sp hybridization, it involves of the 1s and 1p atomic orbitals to produce two sp hybrid orbitals having the equivalent energy. S orbital and p orbital, that is the sp hybrid orbitals. Structure of beryllium difluoride molecule. In this case, beryllium is ground state and excited state. 2s orbital, 1 electron excited in p orbital and sp hybrid. In case of bromine difluoride, the fluorine is comes in these hybrid orbitals. Some key features are the molecules formed are linear and have a bond angle of 180. sp hybridized orbitals has a equal distribution of s and p orbitals characteristics 50-50 percentage. It is also called diagonal hybridization. sp2 hybridization, the combination of 1s and 2p orbitals to form three hybrid orbitals of equal energy is known as sp2 hybridization. Example, boron trifluoride molecule. In this case, boron is ground state 1s2 2s2 2p1, and for the electron of 2s is excited in excited state and electronic condition Bf3. sp2 hybridization is also called trigonal hybridization. It involves the mixing of 1s orbital and 2p orbitals of equal energy to give a new hybrid orbitals known as sp2. A mixture of s and p orbitals formed in trigonal symmetry and is maintained at 120. All three hybrid orbitals remain in one plane and make an angle of 120 with one another. Each of the hybrid orbitals form has a 33.33% S character and 66.66 P character. The molecules in which the central atom is linked to three atoms and sp2 hybridized have a triangular planar shape. This is the 1s orbital, px orbital, pz orbital, triangular planar shape of the sp2 hybrid orbitals. Example of sp2 hybridization, all the compounds of boron, that is boron trifluoride and boron trihydride, all the compounds of carbon containing a carbon-carbon double bond, thylene. sp3 hybridization, the combination of 1s and 3p orbitals to form four hybrid orbitals, equal energy is known as sp3 hybridization. For example, methane molecule. In case of methane, carbon in ground state, in excited state, it becomes sp3 hybridized orbitals. These four sp3 hybrid orbitals are directed towards four corners of a regular tetrahedron, making an angle of 109 degree 28 minute. Therefore, it is also called tetrahedral hybridization. S orbital, px orbital, pz, py orbitals, sp3 hybridize, and tetrahedral shape of the sp3 hybrid orbitals. 1s orbitals and sp3 hybrid orbitals of carbon atom, tetrahedral geometry of methane. These are directed towards the four corners of a regular tetrahedron and make an angle of 109 degree 28 minute with one angle. The angle between the sp3 hybrid orbitals is 109.5 or 109 degree 28 minute. Each sp3 hybrid orbitals have 25% S character and 75% P character. Example of sp3 hybridization are ethane and methane. sp3 hybridization involves the mixing of 1s orbital, 3p orbitals, and 1d orbitals to form 5 sp3 hybridized orbitals of equal energy. They have trigonal bipyramid geometry. Phosphorus pentachloride. For phosphorus pentachloride, the electron domain and molecular geometries are trigonal bipyramid. The electron formation is the form of 3s orbitals and 3d orbitals. sp3d hybridization, 1s orbital, px, py, pz, and 3d, sp3d hybridization shape. The mixture of sp and d orbitals forms trigonal bipyramid symmetry. Three hybrid orbitals lie in the horizontal plane, inclined at the angle of 120 degree to each other, known as equatorial orbitals. The remaining two orbitals lie in the vertical plane at 90 degrees, plane of the equatorial orbitals, known as axial orbitals. Hybridization phosphorus pentachloride, sp3d2 hybridization, the combination of 1s and 3p, 1s and 3p, one s, 3p, and 2d orbitals to form the six hybrid orbitals of equal energy is known as sp3d2 hybridization. For example, sulfur hexafluoride, in case of sulfur hexafluoride in ground state, 3s2, 3p, and 3d, in the excited state, 3s and 3p, 1 electron excited, 2 electron excited in the Da and sp3d2 hybridized orbitals. sp3d2 hybridization have 1s, 3p, and 2d orbitals that undergo intermixing to form 6 identical sp3d2 hybrid orbitals. These 6 orbitals are directed towards the corners of an octahedron. They are inclined at an angle of 90 degrees to one another. Sulfur in ground state, sulfur in excited state, sulfur in hybridized state, sulfur hexachloride, sulfur px, py, and pz, dx square, hybridization, dz square, sp3d2, sp3dt, the combination of one s orbital, three p, and 3d orbitals to form 7 hybrid orbitals equal energy is known as sp3d hybridization. For example, iodine hexafluoride. In case of iodine hexafluoride, iodine in ground state, 5s 5p, in the excited state, and iodine is hybridized state, sp3d3. Iodine hexafluoride exudes pentagonal bipyramidal shape. DsP2 hybridization. DsP2 type of hybridization is seen especially in case of transition metal ions. The orbitals involved in these types of hybridization are dx square, y square, s, and the 2p orbitals. The four DsP2 hybrid orbitals adopt square planar geometry. The square planar complex hybridization involves DsP2, one d orbitals, one s, ns orbitals, and two np orbitals. Any two of nps, npy, and npz are involved in hybridization. For example, in nickel tetracyanide, nickel ions has +2 oxidation state and has configuration 3ds 4s2. Cyanide bond being strong liaison pairs of the on-pair electrons of nickel +2 ion. The hybridization scheme is shown diagram. Orbitals of nickel +2 ion. DsP2 hybridized orbital in the nickel. DsP2 hybridized in nickel. One s orbital, px and pz orbitals, dx square y square orbitals, DsP2 hybridized orbitals. In this complex, nickel second ion is central metal ion which undergo DsP2 hybridization. Outermost shell electronic configuration of nickel, atomic number 3d8 4s2 4p0. In complex, nickel lost 2 ion electrons from 4s orbital to form nickel second ion. Thus, electronic configuration of nickel second ion is 3d8 4s0 4p0. During the complex formation, nickel second ion undergoes excitation where two unpaired electrons 3d orbital pair with each other. Thus, one of the 3d, that is the 3d x square y square orbitals, 4s orbital and 2 4p orbitals are empty. They undergo DsP2 hybridization to form 4 DsP2 hybrid orbitals. DsP2 hybridization. DsP3 hybridization, 1s, 3p, and 1d orbitals of same atom having the nearly same energy mixed with each other to form 4 DsP3 hybrid orbitals. As such, it is result of sp2 and dp hybridization. S orbital, px, py, pz orbital, dz square orbital, valence shell electron pair repulsion theory. In polyatomic molecule, the electron pairs, lone pairs, and bond pairs present on the valence shell of central atom exert mutual repulsion among themselves. They tend to far away from each other as far as the possible. In this way, due to repulsion, they experience minimum repulsion and hence attain maximum stability. This is basic concept of BSC theory. In order to explain decrease in the bond angles, they propose following postulates. Postulate of BSC in the central atom of a molecule possesses only bond pair of electrons, then shape of the molecule is regular. If the central atom of a molecule possesses both lone pairs of electrons LPS and bond pairs BPS, the shape of the molecule becomes irregular. Bond angles in molecule decreases due to repulsion between the lone pairs and bond pairs. The extent of repulsion between different electrons pairs decrease in the order. Lone pairs, repulsion, lone pair, bond pairs, repulsion, bond pair, repulsion. Examples involving BSC theory, BF3 twist to P1, hybridization sp2, number of lone pairs 0, number of bond pairs 3. Since donor atom has no lone pairs, BF3 has regular shape, that is triangular planar. In case of boron tetrafluoride ion, The hybridization sp2, number of lone pairs 0, number of bone pairs 4, shape tetrahedral, bone angle 109.5. In case of phosphorus pentachloride, hybridization sp3d1, number of lone pairs 0, number of bone pairs 4, shape of phosphorus pentachloride trigonal bipyramid, bone angle 90 and 120. In case of ammonia, hybridized sp3, number of lone pairs 1, number of bone pairs 3, sp3 hybridized. This is the ammonia. Shape triangular pyramid, spatial orientation of electrons pairs tetrahedral, in which one position is occupied by bone angle and 109.5 to 107 degree, 48 minutes. In case of water, the hybridization sp3, number of lone pairs 2, bone pairs 2, electron pairs 4. Shape, spatial orientation of 4 electrons pairs tetrahedral, but actual shape is V-shaped or angular or bent. Bone angle 109.5 to 104 degree, 35 minutes. Chlorine trifluoride hybridization sp3d2, number of lone pairs 2, number of bone pairs 3, electron pair 5. Spatial orientation of 5 electron pairs, triangular bipyramid, in which 2 lone pairs occupy equilateral plane, but actual shape is T-shape, bone angle 90. Sulfur tetrafluoride hybridization sp3d, number of lone pairs 1, number of bone pairs 4, electron pairs 5, shape triangular bipyramid, but actual shape is linear, bone angle 101.6. Then tetrafluoride hybridization sp3d, number of lone pairs 2, number of bone pairs 4, electron pairs 6, shape octahedral, bone angle 90. Iodine pentafluoride hybridization sp3d2, number of lone pairs 1, number of bone pairs 5, electron pairs 6, square pyramid, bone angle 90. Sulfur hexafluoride hybridization sp3d2, number of lone pairs 0, number of bone pairs 6, electron pairs 6, shape distorted octahedral, bone angle 90. Xenon tetrafluoride hybridization sp3d2, number of lone pairs 2, number of bone pairs 4, electron pair 6, shape square corner, bone angle 90. Xenon difluoride sp3d, number of lone pairs 3, number of bone pairs 2, electron pairs 5, shape linear, bone angle 90. Iodine heptafluoride, formation of iodine heptafluoride involving sp3d3 hybridization, pentacolor bipyramidal geometry of I have 7 molecule. Bone angle 72, 90, 180, 1.0, 1.7, electron pair 7. Phosphorus pentachloride, 1s, 3p, and 1d orbitals of the same cell participates to give sp3d hybrid with a trigonal bipyramidal shape with bone angles 90 and 120. Example, phosphorus pentachloride. Limitation of valence shell electron pair repulsion theory. The valence shell electron repulsion pair model is not theory. It does not explain or attempt to explain any observation and prediction. Valence shell electron pair repulsion is simple and useful, but does not work for chemical species. First, the idealized bond angles do not always match the measured values. Quantum mechanics in atomic orbitals can give more sophisticated predictions when the valence shell electron pair repulsion is unidentified. Molecular orbital theory, okay, talks about molecular theory. We have already discussed about balancing bond theory and balancing electron reformation theory. The third one theory is the molecular orbital theory. According to molecular orbital theory, all the atomic orbitals of atoms participate in the formation of molecule mix up to form new kinds of orbitals called molecular orbital. So molecular orbitals are responsible for the formation of molecules. It means atoms consist of atomic orbitals, but molecules consist of molecular orbitals. Number of molecular orbitals form equal to number of atomic orbitals mix. The number of molecular orbitals assume that atomic orbitals from the atoms combine to produce new set of orbitals called molecular orbitals. Such molecular orbitals are described by wave functions according to quantum mechanics. Basic principle of molecular orbitals theory: when nuclei of two atoms come close each other, their atomic orbitals interact, leading to formation of molecular orbitals. The atomic orbitals of atoms in a molecule completely lose their identity after formation of the molecular orbitals. Each molecular orbitals is described by a wave function known as molecular orbitals wave functions. The molecular orbital wave function psi is such as psi square represent the probability density of electron charge density. Each molecular orbital wave function psi is associated with a set of quantum numbers which determine the energy and the shape of molecular orbital. Electron fields the molecular orbitals in the same way as they fill the atomic orbitals following the of principles, Pauli's exclusion principle, Wund's rules, maximum multiplicity. Each electron in a molecular orbitals belongs to all the nuclei present in the molecule. Each electron moving in a molecular orbitals has a spin half plus half and minus half. Linear combination of atomic orbital principle of molecular orbital theory. The wave function describing molecular orbitals are obtained by a method called linear combination of atomic orbitals, LCAO. Molecular orbitals are formed by the linear combination of atomic orbitals. Linear combination of two atomic orbitals wave functions are brought about by addition and subtraction overlap of atomic orbitals. Let psi A and psi B are the wave functions of two atoms A and B, and psi molecular orbital be the wave functions of the molecular AB, A plus B, AB, psi A plus psi B, psi molecular orbitals. When two atomic orbitals overlap, the new wave function psi AB and molecular orbitals psi YAMO is formed and can be obtained by the linear combination of atomic orbitals psi A and psi B. Psi AB equal to Yan C1 psi A plus C2 psi B. Yan is the normalizing constant which ensures that the probability of finding electrons in the whole space C1 and C2 are the constant which gives the minimum energy for psi AB. The probability density for the combination of two atoms is given by the square of the wave function. Psi square AB equal to Yan C1 psi A plus C2 psi B whole square. So C1 square psi A plus 2C1 C2 psi A psi B plus C2 square psi B square. If N equal to 1, 2C1 square psi A, the probability of finding electron in A, 2C2 square psi B square, probability finding of electron in B, 2C1 C2 psi A psi B overlap of the atomic orbitals. The larger the 2C1 C2 psi A psi B, it is the stronger is the bond between A and B when there is a higher electron density in the internuclear region and bond is the stronger. There will be the two molecular orbitals as a result of two types of combination as given below. Psi B molecular orbital equals psi A plus psi B, psi star molecular AB equals psi A minus psi B. Equation 3 represents the formation of bonding molecular orbitals. It is formed by the addition of overlap of atomic orbitals. Atomic orbitals having the same sign.